Our new state-of-the-art training facility is an example of how we maintain superior training and technical experience. EAB continues to meet the challenges of a dynamic industry and marketplace while evolving through technology and innovation and maintaining a healthy work-life balance.
Good afternoon, everyone. I'm Sim with AABC, and I'd like to welcome you to today's Staff Talk webinar. I also want to thank our sponsor, EAB Training, for supporting this session. Just a few items to cover before we get started. The presenter will be holding the questions until the end of the presentation, but we encourage you to submit them at any given time using the Q&A button. If you happen to be experiencing technical problems during the webinar, please use the chat function to inform the panelists so that our producer, Will, can assist you. The presentation is being recorded and will be available for viewing in 1 week. In terms of the continuing education credit, everyone in attendance for the full webinar will receive a certificate of attendance sent to their emails within 24 hours. And finally, if you are a certified TBE or TBT, your CEUs for attending this webinar will be automatically uploaded to your respective portals after the webinar. Today's webinar is Troubleshooting Flow Issues of a Renovated Condensing Water System. Please welcome today's speaker, Alvin Beddingfield Jr. With over 15 years at Engineered Air Balance, Alvin specializes in testing, adjusting, and balancing for HVAC systems across a wide range of projects, including K-12 schools, universities, office buildings, research labs, and healthcare facilities. As a project manager, he leads large-scale projects from start to finish, known for his attention to details, strong problem-solving skills, and ability to manage teams while exceeding client expectations. Without any further ado, I'd like to hand it off to Alvin to kick us off.
So today's webinar is the Troubleshooting Flow Issues of a Renovated Condensing Water System. Starting off with some of the learning objectives. Basically, we're going to cover identifying common flow issues in the condensing water systems and basic understanding of how to system design, component sizes, and installation factors of the associated equipment can contribute to the water flow restrictions or possible failures. We're going to also cover enhancing project efficiency through effective planning and coordination, and try to explore some best practices of coordinating with mechanical contractors, engineers, owners, even try to tackle into the end users that will have to utilize the equipment and service it throughout its life expectancy. Evaluating the impact of common sizing, system operations, and how to undersize and drainage can improper flow balancing and coolant tower operations, and then analyzing performance and diagnose flow disruptions, and kind of learn how to utilize pressure drops, measurements, pump curves, manufacturer submittals, and to try to pinpoint some of the performance deficiencies throughout the entire system. So this presentation, I had 3 campuses that we experienced similar problems. They were all what I consider a sister project, but they're all in the same specs, same project team across the board, and they're 3 packaged campuses. They're following in the same kind of renovation, plant renovation, and upgrading the cooling or condensing water systems throughout the system. So the presentation kind of focuses on various challenges encountered during the upgraded process of the chilled water plant of an elementary school. This was actually in 3 different ones that we had. 2 of them had similar problems. One of them was slightly different, but it was the same situation. And details the timeline from the initial startup phase of the project to the project's completion, and highlights some of the obstacles that we covered. As I said, the scope of it was included the installation of 2 new water-cooled chillers and a new coolant tower, and then 2 chill water pumps on the primary one, and 2 vertical lift pumps on the main presentation. And I'll re-reference 2 other schools that had end suction pumps that were isolated from the vertical lift side. So basically jumping into it, we were contacted by an engineer at one of the campuses. The chiller manufacturer was out there and they kept having flow issues. The mechanical contractor went out there to assist. Both of them were having the same similar problems. Chillers would get started up, there'd established flow, and then shortly after flow would just completely drop off, and they couldn't start the chiller. So they spent about an 8-hour day trying to troubleshoot why the chiller won't start up, why it keeps losing flow. So knowing how close we are with the mechanical contractor and the engineer of record, they reached out to us to try to say, hey, is there any way we can come out, take some flow measurements on the equipment to try to isolate the issue, determine if it was, since some of the existing piping was being utilized, to determine if it was existing piping issues, if it was problem stemmed from the design of it, if it was equipment related. They just really couldn't pinpoint it from the conversations with the mechanical contractor and the chiller manufacturer. So we were contacted to go out there and take some measurements for the engineer and try to see if there's anything we can assist with the troubleshooting process to get the equipment started up. So initial arrival to the project, we obviously took a snapshot of what they were experiencing and tried to recycle everything. So we shut down the plant, let everything settle out, and then upon startup of the condensing water system, initial flow would be established. Chiller would actually try to start, and then about 10-15 minutes, 5 to 10 minutes after, flow would completely drop, and then we'd lose the chiller. Another observation while we're completely lost the flow is we've noticed that the tower or the condensing water going over the cooling tower is significantly reduced, knowing that we had some sort of water shortage coming through the system. So we decided to retest it, try to figure out what we were seeing. So to recreate it from what the startup, as I said, we let this system shut off, settle out, and took pressure measurements started up the condensing water system, took measurements across the chiller, across the pumps, strainers, anything that we could take a measurement across to just try to figure out where the flow is. That way we can plot the chiller manufacturer's submittal flows and plot across the pump curves. Just trying to get a snapshot of what happens right when it starts. So once the chillers would start up, and everything would settle out, we left our devices on there and then noticed the flow would completely drop. So we retook measurements across the pump curves and the chiller submittal. And then once we got that, collected that data, we took new flow or compared the flow measurements to realize how much flow we had, how much flow we lost once that isolated low flow condition kept surfacing. So upon our discovery, the team, we observed pressure drop on both chillers and strainers. The strainers are excessive, so that was something we isolated, saying, okay, the strainers needed to be cleaned. They had an above, I think they were at 8 PSI of drop across the strainers when we were actually proving design flow. So that was one thing that we mentioned to the mechanical contractor to try to, hey, the strainers need to be pulled and cleaned because they are excessive. But one thing that we did notice also was the sump basin contained trash bags. And for us Texans, it's either HEB, Walmart, or some Buc-ee's bags that kind of tend to float around in those, in the sump basin. And we believe that was was the primary cause of the flow loss, because we turned off the system again and kind of noticed the bags would float back right to the top of the surface. And then as soon as we deactivate the system, the trash bags would eventually start going below the water surface level. So what we're kind of concluded back to the engineer was, hey, we're believing that the trash bags are being drawn into the inlet pump diffuser. And once it run for 10 to 15 minutes, those bags would just cling to that basket and reduce all the flow restrictions. And that's one of the reasons why I feel like we're getting an inconsistent flow. It's like one time it would be a little bit less, one time it would be a little bit more, and that was just because of how much trash each time. Once the pumps cycle off and it would float up, how fast it would pull it back down to the inlet pump diffuser. So the only appropriate method to address this debris found in the pump basin was to completely drain it and clean the area, remove all the trash bags. And so upon assistance with mechanical, obviously they ran the pumps a little bit, opened up the strainers, let that blow out into the mechanical yard, and by doing so, they actually pulled the strainers at the same time to clean them. But I ended up, I think, pulling out, to my estimate, I wish I had a picture of it, but I think it was about 35 bags of HEB, like just the grocery sacks, and a few water bottles. Obviously, those aren't going to cause that, but it was basically sandwich bags, Walmart bags, just all within that debris. And this was the only approach that we saw was necessary to just eliminate the problem completely. It's just to take all the water out, make sure there's no leftover trash in that basin. Additionally, we noticed that one thing we kind of pointed out to the mechanical contractor and the EOR was, since this coolant tower is in the corner of the mechanical yard, it even comes down to the garbage dumpsters in the same location for the K through 12 campus. There was a good gap. Some points of it was almost near a 6-inch gap around the basin, and our concern was anytime trash would just collect in that corner of the mechanical yard due to wind or blowing in there, naturally from the coolant tower pulling it in anyways, that gap would just allow any sort of debris to actually enter that concrete basin and allow it to collect. And that was something that you could just notice in the mechanical room. Every time the wind blew, trash would just circle around in the corner. And our goal was to try to eliminate that as much as possible. So coordinating with the engineer and the mechanical sub was trying to prevent that. We try to utilize some hardware cloth and some additional stainless steel paneling to try to cover up those gaps as much as possible to prevent any further debris entering the concrete basin. Because obviously once we leave, then maintenance is going to have to try to troubleshoot those issues further along, and that was something we wanted to try to avoid for the client. So our conclusion after that was completing the tower basin. We took all the pressure measurements across the strainers, across the pumps, across the chillers, and realized that, okay, everything seems to be functioning, the chillers are maintaining, so we recontacted the chiller manufacturer. They came out and started up the chillers, no problem. But in between the time when they came out, once we started up one chiller, no issues. Everything was fine, everything was working. We decided to run both pieces of equipment just to make sure there was no other restrictions with that. And we came across the next problem, which we had to address. So what we came across was when both coolant towers were operational, we started pouring water out the collection basin and basically out the overflow out the inlet louvers of the chiller. So obviously our concern was why aren't we draining into the basin, into the concrete sump fast enough, and why are we coming out the inlet louvers? So this one, you look at the manufacturer submittal, which I'll cover, and you kind of go into the manufacturer submittal. You're like, okay, it says it can do the flow, and why are we keep rising? Why do we keep losing water? So what we revealed that the flow rate draining from the collection basin is definitely influenced by the connections of the condensing water pumps, and they have to be sized from what the intent and how those pumps are connected, because there is a limitation of what the tower can do depending on what the pumps are collected. So after examination of the tower, we had a bottom inlet gravity flow with the vortex plate. So that's just the way the tower manufacturer wanted the configuration. So when we examined the collection basin, it was a hole at the bottom. Obviously, it was 8-inch round dropped into the concrete basin. with a vortex plate, and according to the manufacturer's specifications, indicated a potential issue with how efficient we can drain the water out of the tower. So we're going into it, we're gonna take away all the other scenarios, right? Only thing we're looking at right now is the bottom outlet collection, right? That's the only thing that we have. So we're gonna go through the chillers. Obviously, we needed to make sure that, okay, where we designed, are we high? Can the tower handle what the chillers can do, or we have too much flow? So going through it, obviously we took our measurements across the chillers when we were determining the low flow scenario, and came across the scenario, okay, so we're doing 495, and I think we set them up for, I want to say 510, 515. And going into the pumps had a little bit excessive, and they had a little bit of extra curve on them. They're set at 525. We throttled them a little bit just to try to get them closer to that chiller curve. So we set the system up around 510, I think, on one, 515 on the other tower, or the other chiller. But we're gonna go into it with the cooling tower was designed at 990. So we knew that we were right there on the flow. But looking at the in-suction side of what the collection accessories was, it was an 8-inch pumped flow size connection. So going into the 5 scenarios of what we can do, we were sized at the top one of the side end suction, but that's not what we had. So going through each scenario, it's like taking a snapshot. What do we have? What's installed, right? So isolated down was the bottom outlet pump flow, right? That wasn't what it was, but it was gravity flow with or without the vortex plate. Either one can produce the same amount of GPM. So 598. Okay, well, we know now that we're really short of what that tower can actually drain naturally out of the cooling tower. So a snapshot of underneath the tower when we're having that scenario. So obviously chiller 1 and chiller 2, roughing them down back into design CFM to retest this system to try to figure out why we're overflowing and do we have too much. With the tower's capacity, we had a surplus of 392 entering the tower. So basically we could only tank out 598, but we're dumping in the 990 into that tower. So we had excessive water flow that was causing the tower to increase until eventually just overflow up the inlets, because the gravity outlet of that chiller could not drain any faster than what it was capable of doing. So basically a snapshot of the tower. So basically we're coming in at 990 and we're only able to discharge 598. So kind of giving a snapshot of what we would see is basically the tower and the concrete sump would dramatically start to drop, and the basin of the cooling tower would increase, and then that's when it would just naturally roll over, because obviously we could not drain any more than the 598 out of that concrete basin. So that's kind of the situation that we're seeing with that one. So after our review and proposing with the, talking with the engineer of record and the mechanical contractor alongside the mechanical equipment supplier, the importance of this was to maintain the warranty of the equipment. And when we talked with this equipment provider, they said if anything was cut, any hole was repenetrated into that basin, it would void the warranty. And that's the one thing we didn't want to do for the district, was to avoid any warranty that new equipment would be provided, because new equipment, they'll have a 5-year warranty. So limiting the warranty and trying to find an alternative solution to not void a warranty and cause additional headaches to the districts and their investment of the equipment, we had to come up with a solution. So roughly, since we had the supplied end suction connection, right? That was there to begin with. So the snapshot of the picture on the left is how it was installed, right? So obviously the cooling tower was equipped with an additional side 8-inch connection. And the goal was, if we could modify that, reuse that as an additional 8-inch drainage of that tower right back into the sump basin of the concrete basin to avoid penetrating the stainless steel underneath the bottom of the tower. Going back and forth with the engineer, he agreed that was the most invasive method and quite funny method of trying to utilize an additional penetration of our tower. But basically, if we're utilizing an 8-inch gravity fed and we can do 598, well, if we're utilizing a side gravity fed connection, we can do another 598. So luckily that was something we added into it, and it actually worked. I mean, we had no more issues with the overflowing of the tower. We eliminated possible warranty, nullifying the warranty for the district, and we're able to run the showers successfully. So at this point, we finally were able to get the mechanical startup team in there, start up these chillers, try to start pulling the campus in for finishes and stuff like that. But it was a very invasive process of going back and forth. It's like we had flow issues, now we had no water, now we have water, now we have too much water, and trying to eliminate what can we do and what's the next mistake on this job just to get it done. So we thought everything was resolved, right? Okay, everything's fine. I mean, we got flow, chiller manufacturers, everything started up. Well, while maintaining the main problems of the entire system, the three-way valve, and you can probably see in the back picture, the three-way valve was not replaced. So going back into it, okay, three-way valve's back ordered, tower's running, equipment's running, everything's fine. We're in there balancing the rest of the building. We get called back saying, hey, we keep losing flow. We're getting chiller alarms, chiller alarm, chiller alarm, chiller alarm. I'm like, we cleaned the basin. We took away the overflow issues. What can we possibly keep having? So when we got there, obviously, bypass valve was finally installed. Well, upon arriving, we realized that the bypass valve the valve was aligned with one another. The actuator arm was connected directly between them. So taking a spot, obviously, the left side is what's, coming back from the building. Then we have the tower valve to the top right. The bottom one actually goes to the basin. They mechanical disconnected it for the time being, try to help troubleshoot the issue. And then I guess that to the right of the screen is going to the cooling tower. So that's going to going to the cooling tower and going to the top side of the cooling tower. So basically, talking to the mechanical contractor, he confirmed that the valve was ordered the way it is. This is how I got it. This is exactly how it was configured. And talking with him and trying to explain, like, and the water's going to go in, if they're tied together, you're either both open, you're both closed, or vice versa. You could be open and closed, but either way, water's not going to make it through that pipe to get back to the tower, and we're going to keep losing flow. So he met us on site, and we kind of explained to him and showed him the way the piping needed to be reconfigured and stuff. So he brought his team back out there and tried to make modifications. So as I said, when the cooling tower valve was reconfigured and reoriented to try to eliminate that, so we could either go bypass or we can go over the tower. But it was just another complication into the process, right? One after the next. It's kind of like, okay, well, we're going to get there eventually. No, we're not. We're still short. We're going to get there eventually. Nope, we're still short. So it was a headache of trying to use different methods and trying to understand how different things come in at different places at different times, and just a chain of events, and all this on one campus. So going into it, similar situation, different project. Same tower, as I said, it was the same team. This was actually a reference to two projects. We had the same exact issues. Obviously, the lessons learned from the first tower, we can cover them from the second tower. Second tower goes into it where, okay, well, we've kind of made some lessons learned, right? We kind of established all right, let's get a chain of events. Obviously, we're having flow issues at a tower. It's different type of issues, but we're having similar issues. So we already know, okay, well, let's go through the engineering submittal data for the tower again, because obviously that was something we utilize. And circling back with that, that's something that's sometimes I'm not included when they just pull out the submittal. They just give you the performance. That engineering data sometimes has to be dug and go through and try to pull that data to try to actually get the actual capabilities of the tower. We all understand the performance works, but what can the tower do? So in the evaluation of the newly installed condensing water system at this school, problem occurring at the campus offered another opportunity to display our troubleshooting abilities and overcome operational challenges at this school. So going into it, basically you're coming back from the building right here. This is what's coming back from the building. This is your bypass valve. Obviously we're coming off the bypass valve going to the top of the tower. This is that end side of the tower that we utilized on the last project to drain into the concrete basin. And then we're connected to the bottom of the tower, which comes up here and goes to both pumps. And then this is your two downspouts to your pumps. So we're pulling from the bottom of the tower. Okay, so we know we got a different situation. So what are the issues occurring? Well, one, we're having a lot of air being drawn into the pumps, and it sounds like rocks just going off, which we know is a cavitation issue. Another problem is the energy management team saying, hey, we're high water consumption. We're parking lots completely saturated every single morning. We're going through the water meters are going around the clock. And the third issue was constant chiller condensing water flows, which we can establish that's because of the cavitation. We're losing flow, and then we lose flow into our tower. So we kind of already know what that was going on, but let's dive into the cavitation issue and the high water, because that's the two that we know is going to be isolated from the last one. So looking at the two chillers, obviously one was an existing chiller and then one was a new chiller. So let's establish where our flow's at first, right? So we're gonna go into it, and the flow is gonna be, okay, 364 on the first cooling tower, and then we'll dive into the next one at 790 or 750, right? So we got our two flows. Okay, now what's the cooling tower? Once again, let's look at the way the cooling tower is designed. Pump side suction. So, okay, well, that's one flag, right? Because we already know it's piped to the bottom. So that's already a red flag that's setting us off. Like what are the tower's capabilities? We know that we already had the first roadblock. And towers ended up being designed for 1050, right? So bottom flow, no vortex plate. Okay, well, where are we at? Okay, we're not even on the chart, right? We need to be able to pump roughly, which is a little surplus at 1114. We're not even on the chart of what we're connected to. So obviously the piping needs to be completely reconfigured. So contacting the mechanical contractor, met me out there at the project and walked through the engineering submittal and what the tower can do, and identified to him like, hey, the tower's not configured correctly. The piping's completely wrong. Like, we can't be off the bottom. We're not even on this chart anymore of what the tower can actually drain, which is why we are sucking air. We drain that whole tower completely dry, and then there's no water in the back into the pumps, and it just starts going dry, which then gravitates into the chiller. So we got one problem under control. The high water flow is still out there, but we got one thing that we can configure. So upon our discovery, we realized that the condensing water system pumps were improperly connected. This connection was identified as a critical error, in my opinion, since there's no performance limits outlined in their tower's data. So reached out to mechanical contractors saying this needs to be corrected. We're never operating in this scenario. So meeting out them, what's the easiest solution? Okay, well, it was naturally designed for an end suction pump, so we can go with that. And then the two other options, well, reconfigure piping plus The sump, we gotta add a sump, but we really needed that 1014. So we don't even want to dive down the 1090, right? That's just, we're already a little bit limited. Let's not go down that aisle. And the third option would be adding another vortex plate. And on top of adding the vortex plate, changing adding a sump to the bottom of the tower also. So obviously with their idea, obviously what he's gonna jump into, oh, the easiest one is an suction pump. I mean, I don't have to add any parts. So there's a performance for it, we're good. So let's go down that road. So pipes were reconfigured. I know it's kind of confusing the way it was, but obviously you're coming in back from the building, which is where we're coming in from here. We're going down as the bypass underneath, so we're coming up the chiller. So now we're coming off this pipe, instead of coming to the side, we rerouted it to underneath the cooling tower. And then this pipe that's coming from the end suction is now coming into the two condensing water pumps. So, okay, let's resolve the piping. Unfortunately, we still constantly were having a little bit of air enter the system. So while this system approved, we were able to run the new chiller, we were able to run the existing chiller. But once both chillers came online, we started running into a similar issue. We started still pulling a little air into the system. We're still draining into the system. And what the complication was is that tower is spec'd to be able to handle it. Obviously, that basin's really, really shallow. So either the mechanical contractor and even the tower manufacturer had a very difficult time trying to teeter-tot where that overflow had to be set. We'd either go too low and start pulling in air back into the system, and then, okay, we're back at square one, or we raise it up, and then we dump even more water into the street. Because what happened is once the tower would turn on, the water levels would drop. Well, it would fill that tower back up. And then once the tower filled back up, it started draining back into the street. And it's kind of unclear here, but even to the point where their alternative method was to actually take the overflow drain and tilt it up just slightly, just instead of being like 90 out and drop, just to try to get a little bit more capacity out of the tower, to try to avoid the cavitation that the pumps are experiencing. And as I said, one tower would run fine, either the larger tower or the smaller one, or the smaller chiller, the larger chiller. But when both times, we'd still slightly pull air into the system eventually. So what would happen was, as I said, once you fill that overflow up too high, it would basically, tower pump would rise. The water levels would drop once the tower turned on. Once the tower level dropped, the overflow would keep filling. And basically every single night, once you ran all day and it would fill up, once the tower would turn off, it would drain into the parking lot and level it back out to the point where the district was just constantly dumping in water. And this was occurring at two separate projects. So the first project, a sump basin, right? We got a concrete basin underneath, we droned in. Both of these other two schools, the original pipe was identical. So we obviously dived into one school and said, okay, well, the piping's wrong here. Let's go to the next school. Let's say, make sure the piping's not wrong over at this school. Okay, well, the piping is wrong over at this school. So now you've got to reconfigure this piping. Now we're going to circle back. Okay, well, now that the piping's been reconfigured, now we got to go back and set the water flow. Well, this one's getting too low. We're starting to cavitate. So we'll go back to the other school. Yep, we're cavitating over here. So let's raise the water flow. And it was just a nonstop action. Like we resolve one issue at the one school and we'll go to the identical school and say, okay, well, let's tackle the same issue. Okay, well, now we're tackling the same issue. We'll go back to the other school. Here's the next issue. Let's keep troubling. But just having that water nonstop, we try to reach out back out to the mechanical supplier and said, okay, we're just teeter-totting this. We can't figure this. We can't set the basin properly. It's either we're slightly pulling some air in and eventually we lose a chiller randomly. It just get a little pocket of air into the pump and cavitate and lose flow, or we're just dumping out water and wasting chemicals and wasting the district's water connection or water service to the tower. So it was around and around, back and forth. So going back into the tower, we decided to reach back out to the tower manufacturer and said, okay, what can we do? Like, we have the third option of adding the sump and the vortex plate. Obviously, we can't just add the sump, so we got to add both. So consulting with the manufacturer, the easiest solution was, hey, let's add the capacity. Let's just add the sump at the bottom of the tower. It'll add a little bit of capacity to it. That way we have that once the water goes down, it was another way of doing it. So sadly enough, now we're going to try to read back. So we'll go back to this chart, right? So now we're sump flow. So now that we've configured the tower, now we got to reconfigure the tower and change all the piping again, which means we got to change all the piping again at another school. And it was just around and around trying to solve these issues. And like, well, we went with the easiest solution. Well, it's not easy, is always not the best option. So reaching back out with them, they said, hey, this is going to be the easiest thing, is to add the sump, and it's going to add a little bit of capacity at the bottom. The pump's going to pull from it, which allowed us to really adjust that makeup water correctly and allow those pumps to pull from that sump basin rather than the side. Because at this point, obviously the sump's at the lowest point, so you're not going to be able to pull the air anymore. And it allowed once we got the operating level, we were able to set the autofill onto that valve and really try to establish that. Because as I said, it was going back and forth, like, okay, we got this issue, here's the next issue. And terribly enough, I felt terrible for the mechanical contractor, because refiguring piping is not easy. So he's on an overnight crew. Issues established. All right, school's out. Cut the pipe, re-weld it, reconfigure it. Round 2, turn it off, cut the pipe, reconfigure it. Round 3. And it's not an easy task to keep having to break all your welds and recut and redo all your piping and ordering all the correct fittings every single time. But luckily, he knew the end goal was to satisfy the client and go from there. Just a little bit of reworking with us, trying to work through it, because obviously the goal is to try to take care of the client to the fullest. So obviously, after all these projects, we thought we got 3 towers now working, 3 towers no overflowing, 3 towers not having chiller alarms. So circling back to the whole group within the district and the EOR, we're able to avoid all these issues. It was a little bit painful going through it, but we believe that it provided us a unique opportunity to try to express and showcase our technical expertise and our troubleshooting abilities, and utilizing means and methods and pump curves and performance data, along with taking our measurements and diving into it a little bit deeper. As I said, you get the submittal, and the submittal process shows the performance data, but you don't always get the engineering data. And trying to figure out, okay, well, why do we have this issue? And then what's the next issue? And what's the next issue? And so on and so on and so on. What can we do to help the situation? Because we don't want to avoid a warranty. We don't want to keep losing water. And sadly, I don't want to force a mechanical contractor to try to repipe it. But the overall goal total was to have a successful chiller and have a process where maintenance doesn't have a nuisance calls and service disruptions to school, and just all these unique challenges that just kind of stemmed and all in one summer. Like, these are all sister projects, so these are all simultaneously as they're going on. So you're just doing chiller troubleshooting for a good part of a month and bouncing between. Okay, well, we're good. This chiller hasn't had any issues for like a week. Oh crap, we're right back where we started. Okay, circle back. We gotta go back to it. Like, there's one thing after the next, and I think it provided a unique opportunity. It was a good learning experience for my guys, and it gave us some lessons learned to the point where just because the submittal shows it, there might be a miscommunication somewhere, and trying to troubleshoot the the bags that would constantly float up into the basin. Like, it'd be one time you'd run that chiller for, 30 minutes, you'd have no issues. And then one time it'd be 5 minutes and suddenly the bags would cling. So trying to figure out ways of quickly troubleshooting these things and learn this is an experience of when I have a flow issue of the tower, first thing is I'm going to start taking something down in that basin and see if I start finding trash bags, because it's something that was just not the first thought on my mind. It was like, okay, well, why are we keep losing flow? There's a trash bag in the sump basin. So I think it was a good lessons learned. I think it gave us a unique opportunity to try to showcase our troubleshooting ability and working with these contractors, and some sort of pride of how well people are able to work as a team to try to get to the solution at the same time. So, but after that, I will roll into questions. I don't think I'm too far ahead. I do talk fast, but I think I'm tracking pretty decently.
Perfect. Thank you so much, Alvin. Now is the time for everyone to go ahead and drop your questions in using the Q&A button. I do see one question right here. So the person says, was the flow rate meant to be condenser side, not evaporator side?
No. On the flow rates were designed on the condensing water side. Because right here on both chillers, this is going to be your condensing water flow, and this will be our actual flow for the evaporator side. So both towers were designed for the condensing water flow.
Got it. Thank you so much. Next question for you is, regarding the overflowing tower that you mentioned, it was designed for an end suction connection, but bottom flow gravity was used instead. So do you know if the tower supplier was aware of the pump configuration during the tower selection process?
So this is kind of a unique opportunity. It's a good question, but the unique opportunity is after going into the conversation with the team, the towers originally were spec'd on these projects to be refurbished. All they wanted to do was to refill the towers and just leave the existing towers. The mechanical contractor decided, saying, hey, instead of doing a 1-year warranty with the fill, I can give you a 5-year warranty with a new tower. And roughly for almost the same price, like the price per the tower and the price for the fill was roughly close to the way he was able to purchase these chillers. So I feel like since the two were identical, I believe the way the tower, after talking to the supplier, was, hey, we thought all three of these campuses, the way it's explained to us, were the same. So the overflowing tower was kind of a unicorn into the fact they were assuming, since they were 3 identical buildings, the 3 towers were identical, and it was just a miscommunication on the concrete basin tower, because they were on the assumption that all 3 towers were the same. As I said, these were kind of a different scenario because it was a rush to try to get the towers in, since they were supposed to be just fill replacement, but since they were new towers, they just had a miscommunication between the 2 sister campuses and the overflowing campus.
Interesting. Thank you so much. The next question for you is, what signs indicate a misbalance or improperly sloped pipe system?
Can you repeat the question?
Sure. The question is, what signs indicate a misbalance or improperly sloped pipe system?
Just say flow system. Can they clarify that a little bit? Because I mean, the towers were balanced.
Got it.
I don't understand the slope part of it.
We can get back to this one.
Okay.
Let me move on to the next question. That is, what do you believe is your biggest lesson learned after your experience with these condensing water systems?
The biggest lesson learned is to also, it was a lesson learned of trying to learn how to troubleshoot the systems. The second part of the lessons learned is how important it is to reference not just the submittal, but the engineering and the tower's capability specifications. We typically go through a performance side of the equation, but we don't typically dive into the engineering specs. I think this is unique lesson learned because theoretically we assume that, hey, if we get our flow, is there a possibility that, do we know if the engineering specs of the tower capability is there? And it's something that now I reference every single time, like, okay, I want to know how close I am to that threshold. Like if it's designed for 1300 CF or 1300 GPM, and this connection's, 1400 or 13 and a half, like I want to know how close I am to that threshold. So I think a good lesson learned was looking at every piece of data and every limitations of every single data is essential, because that possibility of just, hey, your tower's your chiller's a little high, or your makeup water's not properly set, could cause overflow issues. So knowing that to reference more just the submittal, but going into the tower specifications and trying to find those limitations and bring a different significant value to the overall execution of a project.
Perfect. Thank you so much. The next question is, how do you recommend coordinating with controls contractors during renovation projects to ensure proper flow verification before system startup?
That's a tricky one, but I'll dive into that one. So it is with the controls contractor on certain things. It goes into, even with the evaporator side, is to try to coordinate with them, and during the flushing process to try to make sure they have all their valves open correctly. It comes down to the selection process, even as I said in the implication of the towers, like since they were utilizing existing piping, they ordered the valve off of the same different configuration than the tower had said, because as obviously if I go back to this slide, they ordered all three of them the same because they were on the same impression that all three towers were the same, and trying to coordinate with them saying as early as possible. We know that the valve was back ordered, so they try to order quickly, but knowing what pipe configuration, and it might be with them coordinating with the mechanical contractors, like, are we going to use new pipe? We're going to change the configuration, but trying to just open the lines of communication total as a group. As I said, we're all a team in the same process, and the more we communicate, the more it's transparent at the project, the better that we're going to have functionality through it.
Perfect. Thank you. Just so that everyone knows that we still have 10 more minutes remaining for questions. So if you have any questions, please use the Q&A button, and that way you can ask the question to Alvin directly. Alvin, the next question for you is, can you shed some light on the simple ways to check if the pumps are working properly? This is something you might have already mentioned, but just simple ways for everyone to just keep an eye out or look out for how they can figure out if the pumps are working properly.
Yeah, so I mean, there's multiple ways. One, check the pumps are operating correctly. Obviously, we're always going to cover the basis of, is it rotating the correct direction, right? And listening for sounds, like as I said earlier, it sounds like there was grind or dirt or mixing concrete, and it's sounds in the plant that you start hearing like a high-pitched noise from the pumps. There's a lot of pumps to make sure it's operating properly is usually tied to a sound, in my opinion. It's knowing the sounds that you hear while the pumps are running. Obviously water's moving, but grinding sounds and high-pitched sounds, like, okay, well, we might have a flow restriction, or the grinding sound, we might be cavitating, we might have air into the pipe. And I think the easiest way is obviously, one, watching the gauges on the pump. Do they bounce? Are they kind of like, do they stay smooth? And or putting your water meter onto the enter suction side of the pump, and does it stay stable? My thing with plants is immediately what I hear is sound. Everything I go off of is a sound thing first. I'm trying to listen for some I can't say the word. I'm not even gonna go there. Something that doesn't sound right inside the piping. Does it sound like sand or concrete? Does it sound abnormal, I guess you'd say, from a typical plant? So the first thing I would say is, if it's running properly, is always by noise. And knowing the way a mechanical system is running, the way the water is supposed to sound, is key. And the more plants that people experience, the more it's going to come natural to them of trying to hear for M&L. And I said it just right the first time, but hear those sounds that institute something wrong with the system. Second thing would be is watching the gauges. Do they bounce? Do they stay stable walking into it? And then obviously the measuring flow would be the other way to diagnose the system.
Perfect. And this would be the last question, unless somebody else has any question. This would be, how do you recommend handling existing piping that does not match modern equipment flow rate requirements?
So hopefully some of that can get caught on the design review on the piping. I guess the way the question should be worded, if it's undersized piping. But that is going straight to we'll go straight to the engineer. If we see where there's a piping restriction, or they put a weird flange to the piping, it's opening that communication directly with the mechanical contractor and the engineer and saying, hey, this looks something that we spotted. A lot of the times we have a lot of success doing that during observation walks. We try to get to the jobs early as possible. We're kind of to the point where on mine, if I know a welder's out there welding, it might be the existing plant, but if I know something's going on at the campus, I'm trying to get there to spot when the pipe's dry, why he's roughing it in to try to get it set, and trying to catch those issues earlier. Going into after the fact, if it was, hey, we replaced the chillers, but we didn't replace anything else, that's something that needs to be caught also as early as possible. But those will go directly to the engineer of record and try to say, here's what we do. I've had jobs where I'm giving him the velocity per second through the pipe and saying, hey, you're a little high here, or the newer equipment is a little bit larger than the existing equipment. This is what the pipe velocity was. This is what the pipe velocity is now. And try to give it and explain it to him in numbers where it's an easier suggestion of, do we need to change it? Or, hey, is it just enough that we think we can try to push it? But trying to address those issues earlier as possible with the engineering team and the design team to try to overcome those obstacles early.
Thank you so much, Alvin. And that looks like it covers all the questions that we received. And with that, we can wrap today's webinar. Thank you so much again, Alvin, for the excellent presentation and the discussion. And thanks again to our sponsor, EAB Training. Alvin, can we move to the last slide for this one?
Yes.
Thank you so much. Last but not the least, thank you all for joining us today. Before we wrap up, make sure to save date for the 2025 AABC annual meeting. We're headed to the sunny Amelia Island, Florida from October 22nd to 24th for our 60th anniversary celebration. Meet and connect with 150 plus test and balance and commissioning professionals from across the country. You can learn more on aabc.com. Thank you again, everyone, for joining. And Alan, if you want to go ahead and share your information that we skipped past before this one, if in case you have any questions for Alvin or need to get in touch with him, that's his information up there. Thank you so much. Thank you, Alvin, and thank you, everyone, again. You all have a great day.
Thank you.